Radiation hardness assurance encompasses comprehensive test methodologies for evaluating the performance of electronic components and systems under the influence of radiation. It addresses several radiation-induced phenomena, including ionizing dose, displacement damage, and single-event effects. These phenomena pose significant challenges as electronic structures continue to miniaturize, influencing their susceptibility to radiation effects. Hardness assurance verification testing is a critical quality control process used to confirm that a material or component meets specified hardness standards. HAVT was conducted by quality control personnel at AUTONETICS. Hardness assurance verification testing for the Minuteman missile system, a critical component of the U.S. nuclear deterrent, is an elaborate and ongoing process. It extends far beyond a single test, encompassing the entire life cycle of the missile and its launch facilities to ensure they can survive and function during a nuclear strike and other threats. This testing addresses multiple threats, including radiation, electromagnetic pulse, or EMP, and the physical effects of a nearby nuclear blast. The HAVT types of tests are gamma testing at Physics International with Pulserad 1550 Superflash X-ray at San Leandro, California, and later the Air Force Weapons Laboratory FX-100 at Kirtland AFB, New Mexico. Long pulse gamma testing was at White Sands Fast Burst Reactor at White Sands Base, New Mexico. Neutron total dose testing was at NORTHROP Corporate Lab, Hawthorne, California. And parts testing was at the EG&G LINAC in Goleta, California. Minuteman hardware types tested were parts, which included parts from the D37 computer, the MGSC, and the P92 assembly parts. Modules from D37 computer, MGSC, P92 assembly modules. The Minuteman systems tested were the Missile Guidance Set, NS-20, and the C604 Programming Group Console, Guidance Control Panel. HAVT testing sequence was round 1, starting in 1970 with 3 cycles per year. All modules and systems received a full factory functional test and then another functional test after each test and after multiple total dose neutron tests. After each cycle, test results were presented to the Hardness Assurance Review Board, which included Air Force General, AUTONETICS Chief Engineer, Engineering, Quality Control Managers, Test Engineers, and 2 TRW Air Force reps who were very demanding. And one acted like Columbo, the TV trench coat detective, just observing the whole meeting, and at the end putting 2 facts together showing AUTONETICS failures. Some arguments continued out of the building into the parking lot. Our chief engineer was very aggressive and argumentative and crude. He was an engineer and also a lawyer. He could argue anything. He rolled his own cigarettes, and when arguing, those cigarette ashes would fall off onto his white shirt and cause fires as he fiercely argued with TRW face to face. The Minuteman III missile is the only land-based intercontinental ballistic missile, ICBM, currently in service with the U.S. Air Force. Serving as one leg of the U.S. nuclear triad, it's a key component of the nation's strategic nuclear deterrent. Key features: 3-stage solid fuel motor. The missile is powered by 3 solid propellant rocket motors, which allows it to remain on high alert for extended periods without the need for fueling. Silo-launched. Minuteman III missiles are housed in hardened underground silos for protection and are controlled from remote underground launch control centers. Multiple warheads. When first deployed in 1970, the Minuteman III was the first U.S. missile equipped with multiple independently targetable re-entry vehicles, MIRV, allowing a single missile to carry up to 3 warheads to strike multiple targets. However, under arms control treaties, the missiles have been demerved and now carry a single warhead. Hypersonic speed. The missile reaches a maximum speed of roughly Mach 23, or about 15,000 miles per hour during its terminal phase. Inertial guidance. A sophisticated inertial guidance system, which was upgraded and modernized in the early 2000s, ensures high accuracy. Both the D-37DD computer and the MGC are designed and programmed to control the Minuteman III missile throughout the powered portion of flight. After thrust termination, they also control the post-boost vehicle for the re-entry vehicle deployment phase. In addition, they control the alignment of the inertial platform and test and monitor the GNC systems and other components to determine continued readiness while missiles are in alert status. When a launch is commanded, a complete retesting of the GNC system is made prior to entering the flight program. During flight, the computer uses missile attitude, change of attitude rate, and velocity signal inputs to solve a series of guidance, steering, and control equations. It also generates missile steering commands and controls staging and thrust termination. Finally, the computer determines whether or not to provide pre-arm signals to the warhead. The pre-arm decision is based on flight safety checks made during powered flight. The D-37C computer was built from 22 different integrated circuits custom-built by Texas Instruments for the Minuteman project. These chips ranged from digital functions such as NAND gates and a flip-flop to linear amplifiers to specialized functions such as a demodulator or chopper. Texas Instruments sold the Minuteman series integrated circuits on the open market, but the chips were spectacularly expensive, $55 for a flip-flop, over $500 in current dollars, and not as popular as TI's general-purpose integrated circuits. The circuit boards were very complex for the time, with 10 interconnected layers. Each board was about 4 inches by 4.5 inches and held about 150 flat-pack integrated circuits with components on both sides. The growth of the integrated circuit industry owes a lot to the Minuteman computer and the Apollo guidance computer, both developed during the early days of the integrated circuit. These projects bought integrated circuits by the hundreds of thousands, helping the industry move from low-volume prototypes to mass-produced commodities, both by providing demand and by motivating companies to fix yield problems. Moreover, both computers required high-reliability integrated circuits, forcing the industry to improve its manufacturing processes. Finally, Minuteman and Apollo gave integrated circuits credibility, showing that ICs were a practical design choice. The Minuteman III used the D-37D computer, which had about twice the disk capacity, 14,137 words. The layout is similar to the D-37C, with the disk drive on the left and the power supply on the right. Since the computer is mounted upside down, the boards are not visible inside, blocked by the interconnect board. Note the use of flexible PCBs, advanced technology for the time, soldered with low melting point indium and tin solder. The Minuteman Guidance Set Control, MGSC, contains the electronics to power and run the Inertial Measurement Unit, IMU, providing the interface to the computer. The MGSC handles the platform servo loop, accelerometer servo loops, gyro torquing, gyro compass torquing and slew, and accelerometer C is powering the computer's hard disk, three-phase power at 27.25 volts. The amplifier provides the interface between the computer and the rest of the missile. The amplifier sends control signals to the missile's 4 stages, controlling the engines and steering. The electronic circuitry from the Minuteman I nozzle control units was moved to the amplifier, simplifying maintenance. Moreover, the Minuteman has explosive ordnance in many places, ranging from small squibs that activate valves to explosives that separate the missile stages. The amplifier sends the high current 30-amp signals to detonate the ordnance while monitoring the current to detect faults. The amplifier acts as a safety device for the ordnance, blocking signals unless the amplifier has been armed with the proper code. The amplifier sends and receives signals through the umbilical cable from the ground equipment. The amplifier is constructed as 2 stacks of 6 circuit boards on top of a double-width power supply board. At the top and bottom of each board, connectors with thick cables connect the boards to the rest of the system. Each board is a multi-layer printed circuit board. Texas Instruments flat-pack integrated circuits on this board, the tiny white rectangles, valve driver board, 3 servo amplifier boards, and an ACTR control board, whatever that is. The system board is visible on the left with large capacitors and precision 0.01% resistors. To its right is the decoder board, presumably decoding computer commands to select a particular I/O device. Note the extensive use of Texas Instruments flat-pack integrated circuits on this board, the tiny white rectangles. The Triga reactor is a pool-type reactor that can be installed without a containment building and is designed for use by scientific institutions and universities for purposes such as undergraduate and graduate education, private commercial research, non-destructive testing, and isotope production. The Triga reactor uses uranium zirconium hydride fuel, which has a large prompt negative thermal coefficient of reactivity, meaning that as the temperature of the core increases, the reactivity rapidly decreases, so it is highly unlikely, though not impossible, for a meltdown to occur. Triga was originally designed to be fueled with highly enriched uranium, but in 1978, the U.S. Department of Energy launched its Reduced Enrichment for Research Test Reactors program, which promoted reactor conversion to low-enriched uranium fuel. History. The Triga reactor was developed to be a reactor that, in the words of Frederick de Hoffman, head of General Atomics, was designed to be safe even in the hands of a young graduate student. Edward Teller headed a group of young nuclear physicists in San Diego in the summer of 1956 to design a reactor which could not, by its design, suffer from a meltdown. The design was largely the suggestion of Freeman Dyson. The prototype for the Triga nuclear reactor, Triga Mark I, was commissioned on 3 May 1958 in San Diego and operated until shut down in 1997. It has been designated as a Nuclear Historic Landmark by the American Nuclear Society. Mark II, Mark III, and other variants of the TRIGA design have subsequently been produced, and a total of 35 Triga reactors have been installed at locations across the USA. A further 35 reactors have been installed in other countries. Many of these installations were prompted by U.S. President Eisenhower's 1953 policy of Atoms for Peace, which sought to extend access to nuclear physics to countries in the American sphere of influence. Consequently, Triga reactors can be found in such diverse locations as Colombia, Austria, Finland, Slovenia, Italy, Japan, Malaysia, Bangladesh, Congo, Brazil, Germany, Philippines, Puerto Rico, Vietnam, Mexico. Exposure cell. Test Director Stephen Poole in front of reactor door. Northrop staff setting up in cell. Stephen Poole observing 5,000 Curie cobalt source, remote control arms. Reactor door closed. Paraffin shields. Staff setting up flight control test. Instrument Area Flight Control Testing. Larry Acklin, QC Test Engineer. TERST Director Stephen Poole at Tektronix Dual Beam Oscilloscope in Single Sweep Mode. Note, Larry has a fake technical book in front of the book he is reading. Stephen Poole taking a nap in the wrong place. P93 Flight Control Module Test Adapter. Note, dosimetry taped on module. A sulfur-neutron dosimeter product is a measurement method used to determine the fast neutron fluence, or flux, in high-intensity radiation environments. The dosimeter itself consists of Dosimetry included sulfur round metal disc cups, 1-inch diameter by 1/4 inch high. These were for neutron dose. For gamma radiation dose, we used TTLD dosimeters, tiny Teflon luminescent dosimeters, in aluminum cylinders 1-inch high by 3/16 inch diameter, with plastic screw-on lid. Thermoluminescence, the TLD, uses special crystals, typically aluminum oxide, that trap electrons in a higher energy state when exposed to radiation. When the dosimeter is heated in a lab, the stored energy is released as light, which is measured to determine the radiation dose. The TTLD dosimeters used special crystals embedded in Teflon and then punched out tiny discs, or we used crystal powder in plastic cylinders. The test modules were to be chosen at random from the production line, but the reality of production was that the only available modules were still in production. We would finally get the test specimens late Friday, just before we were about to leave for testing. In our first cycle, myself and Larry Acklin went to pick up the modules, but AUTONETICS was a firm union facility. Engineers who were salaried could not touch hardware. We picked up the modules from the supervisor and started walking to the exit gate. Larry looked behind us and said, "Uh-oh, they are following us. Walk faster." Soon we were running. Behind us was a group of union workers. We got to the gate, but because we had white badges, we could freely exit the building. The union workers had yellow badges and could not exit until end of shift. As we looked back after exiting, we saw an angry group of union workers. P92 Test in Cell. P92 Test Console and Tektronix Dual Beam Oscilloscope with Polaroid camera set for single beam recording of radiation results. Herman Mueller setting up one of many dual beam oscilloscopes.